Alright friends, welcome back. In this video I'd like to go ahead and cover section 3.3 of your textbook, and it's going to seem a little bit odd that we are taking a break from the usual polynomial jargon to now talking about how to divide polynomials, because where we came from in the past couple of videos is we were trying to find zeros of polynomials, we were trying to create graphs by hand, and it seems a little odd that we're going to take a little bit of a detour and talk about dividing, but this is actually going to be an important concept for taking care of examples where we want to do everything we did in the last video with graphing and finding zeros and that kind of thing, but with examples that actually don't factor, and so we're going to need to know how to divide polynomials to take care of that case. Okay, and so we're going to talk about two different ways to divide polynomials in this video. We're first going to discuss long division, and then later on we're going to talk about synthetic division. So getting into long division first, striking some terms here, we like to call the polynomial that we are dividing, we like to call that the dividend. The polynomial that we are dividing by, we call that the divisor, of course. You're going to hear me throw these terms around in the video interchangeably. And of course, if I want to divide one by the other by long division, then of course we're going to use our classic long division symbol. And we just need to go ahead and make sure that we are familiar with the algorithm that we would use to go ahead and actually execute the long division here. So the idea here is this. We want to go ahead and take a look at how we can get the first term of the divisor to identically match the first term of our dividend here. That's the first step. Okay, so when we are thinking about what we need to multiply by, we're going to need to take that x and multiply it times something to make it look like 6x to the third. Okay, and so we are, of course, needing that coefficient of 6, and because we already have one x out here, we are going to need to multiply times 2 more in order to identically match the 6x to the third. Okay, and so that is going to be the first term of our quotient is 6x squared. Okay, and then the idea of what to do next in the algorithm is to go ahead and distribute the 6x squared to both terms of your divisor, and then you're going to go ahead and write the result right here below the first two terms of the dividend here. Okay, and so let's go ahead and actually do that, right? So 6x squared times x, of course, is going to give us the 6x cubed, and again, we did that on purpose so that those would identically match. You're going to see why in a second. And then 6x squared times negative 2 is, of course, going to give us negative 12x squared. The next part of the algorithm here, of course, is to go ahead and take the result and subtract it away. And so you can see here that the reason that we went ahead and tried to get them to identically match is because the x cubed terms are basically going to cancel out and create 0 for us. And now we just need to go through and actually execute the subtraction here with the x squared terms. Now, one important note is that what is going to create a lot of errors for certain students is that they're not watching the signs, right? So just be aware that we're taking a negative 19 minus a negative 12. And so because we are subtracting a negative, that operation becomes addition, and so this is really negative 19 plus 12, and of course that's going to give us negative 7x squared, okay? And then what we would do next is, since we have two terms in our divisor out here, we need to be able to match up to two terms as our result, so I'm going to go ahead and drop down a number of terms until what I'm looking at is the same number of terms as our divisor, and that's 2. So I'm just going to go ahead and drop down the 16x here. And then we repeat that process, okay? So the algorithm dictates that we repeat that iterative process all the way until we run out of terms to work with here. So we are now going to go ahead and look at the first term of our new result right here, which is a negative 7x squared, and ask ourselves what we would need to multiply x by in order to get that, right? So we are missing that coefficient of negative 7, and we already have 1x, so we're going to need to do to multiply times an extra copy of x to get up to a negative 7x squared, right? And so distributing that in, we're going to get negative 7x squared, just like we intended, and then negative 7x times negative 2 is a positive 14x. And of course, we were going to go ahead and subtract those results here. So again, the way that we did this was on purpose so that these x squared terms would cancel out for us when we subtract. And now we're just going to go ahead and subtract those x terms. So that's going to be 16x minus 14x. Of course, that's going to give us 2x. And we're going to go ahead and drop down the next term of our dividend here so that our result is 2 lines long. And we end up with 2x minus 4. Okay? And so now we, again, repeat that process, right? So we now need to go ahead and match up to a 2x, and that's pretty easy to do considering that what we have outside is x, and so we just need to go ahead and multiply times that additional copy of 2. So distributing 2 in, of course, we're going to get 2 times x is 2x, 2 times negative 2 is negative 4, and then when we subtract here, you'll see that everything is going to cancel. Not only do your x's cancel, but your constants also cancel here for us, and we are just simply going to be left with 0. And that number that we leave over with, that is always going to be the remainder of our division. Okay, so because that remainder is 0, it looks like these polynomials divided evenly, and our quotient is right up there at the top. Okay, so our quotient here happens to be a 6x squared minus 7x plus 2. Here in the next example, we're going to see that same process repeated, but one quick special note here about a problem like this is that whenever you are missing terms of your standard form, you're going to need to introduce some placeholders for those missing terms, okay? And so you can see here our dividend looks like x to the third minus 1. I've gone ahead and rewritten that as x to the third plus 0x squared plus 0x minus 1, having some placeholders there for the x squared term and the x term. Other than that, this is going to be the exact same process, so I'll just go ahead and demonstrate that real quick. I believe we just need to go ahead and introduce an x squared. That's going to get these x to the third powers to match up, and then, of course, negative 1 times x squared is negative x squared. And so setting that up and subtracting, we do see that we have a double negative here, so that is going to be a positive 1x squared. Drop the next term down, that'll be plus 0x. And then we just need to go ahead and make sure to multiply times an x to get these x squareds to match up. And so x times negative 1, of course, is negative x. And then we subtract, right? So again, another double negative there, so 0 minus negative x, that's going to give us positive x, and then drop down the next term, that's going to be minus 1. And so what we have is our divisor is identically matching the result that we have here in this line. So we just need to multiply times a positive 1 in order to keep that maintained. So x minus 1 is what we will multiply by, and then of course when we subtract, we end up with a remainder of 0, meaning that these polynomials divided evenly. So your quotient here in the problem is going to be this polynomial right here. It's going to be x squared plus x plus 1. Okay, another example here with some longer polynomials. It looks like our divisor is a trinomial here as opposed to the past two examples where they have been binomials, 2 terms. But it's still the exact same game. We still want to go ahead and match up what we have out here as our first term, which is an x squared. We want to match that up to a 2x to the fourth and ask ourselves what's missing, right? So what's missing, of course, is that coefficient of 2, and we have 2 x's, but we need 2 more to get up to 4 here, so I'm going to go ahead and introduce those extra 2 x's there, and we're going to go ahead and distribute that into our trinomial divisor here, right? So we're going to have 2x to the fourth plus 4x cubed minus 6x squared when we distribute that in. And then, of course, when we subtract, we see here that your x to the fourth terms cancel. Your x to the third terms actually cancel here as well. And what you're simply going to be left with here is going to be negative 5 plus 6x squared, and that's going to give you x squared here. And then one of the things that I want us to make sure that we remember, again, is that since your divisor has 3 terms in it, we're going to need to drop down a number of terms until we match the number of terms of our divisor here. So not only are we going to drop down the plus 3x, that would only be 2 terms in our result there. We're going to need to drop down the next term here as well. So minus 2. All right, and you can see here again, if I'm trying to match up the first terms of both of these, I'm going to need to match up an x squared with an x squared, which just means I need to go ahead and multiply through on my divisor by a 1, in which case I just end up with another copy of the divisor that I'm going to go ahead and subtract here from the result line. So let's go ahead and do that, right? So I'm going to have x squared minus x squared. Those cancel out for me. I have 3x minus 2x. That gives me a single copy of x. And then watching the signs here, I have another minus negative. Negative 2 plus 3 is what that would be interpreted as, and that, of course, would be a plus 1, okay? And so don't forget that we don't have any more terms to drop down, so this expression right here does represent our remainder in the problem, and we just need to make sure that we are aware of how to go ahead and write our final answer when the remainder is not 0, okay? So I've written that up here. The way that you'll always write your answer, since your answer is called the quotient, we're going to go ahead and write our quotient plus the remainder over the divisor, okay? So because the remainder is not 0, this is the way that we're going to go ahead and write our final result. So our final result is the following. We had a 2x squared plus 1, and then we're going to tack on a plus the remainder, which was x plus 1, over the divisor, which of course was x squared plus 2x minus 3. And that will represent our final answer after this long division here. So just making sure that we are aware of those situations where the remainder does not turn out to be 0, we know how to write our final answer. So moving right along, another type of polynomial division is what we call synthetic division. And we call it synthetic because it is a little bit of a shortcut method for being able to divide 2 polynomials in a special case. And it's a shortcut method because we're not actually going to be looking at any of the variables here. We're just going to be specifically working with the coefficients and constants of the 2 polynomials that we're working with. So How do you know you have the green light to do synthetic division? Well, that's right here. You have the green light to do synthetic division, but only if your divisor looks like this. It looks like x plus something, right? X plus some number. And so, again, what you're looking at here is the leading coefficient of this polynomial, of course, is a 1, and the degree of this polynomial is also a 1. Okay? If you've got that going on, then you have the green light to do synthetic division. So you'll notice here in this example that what we are dividing by is going to be this polynomial right here, this x minus 3. Does that look like x plus something? Well, it doesn't look like it right now, but we can rewrite it as x plus negative 3. Okay? And so it's going to be important that we write it like that because it's going to be whatever this number is right here that we're going to be using in our synthetic division. Or in other words, if you wanted to think about it this way, you could. Just take your divisor and set it equal to 0, and then solve that little mini equation. You would add 3 to both sides, of course, and get x is equal to positive 3. Okay? Now, we actually do need to figure out what this number is because that comes into play whenever we actually execute the algorithm of synthetic division, because I'm going to take that 3, and you can see that I've written it over here in a little bit of a box, or I should say maybe a little bit of a half box there. And then you'll notice what I wrote was the coefficients and the constant of my dividend here, right? So I've got the 5 present and accounted for. I've got the, that should actually be a negative 18, so I'm glad I caught that. You have a positive 7 there, and then you have a negative 6. I've just gone ahead and written all of the coefficients and the constant of my dividend, and then I wrote that 3 that I got from solving that little mini equation in a little bit of a graphic organizer there. And so the way that synthetic division works is that there's a little bit of a mapping of the numbers here that we just need to be aware of. And so let's just kind of go over that mapping right now, right? So the first step of synthetic division, once you set it up like this, is you're first going to go ahead and drop that first number. So it's going to be a positive 5 that we drop. And then after that, the iterative process is this, right? We're going to take our number 3 that we have out here, and we're actually going to multiply it times whatever number we have in our result line. And then whatever the result is from that, we're going to go ahead and write that as the next entry of our iterative process, right? So 3 times 5 is going to give us a positive 15, and so there's where we would go ahead and write that result. And then what we do then is we just go ahead and add the columns there, which is why I have that plus sign in the circle. So negative 18 plus 15, of course, is going to give us negative 3. And now because we have a new number in our result line, we're going to go ahead and repeat that process. And we're just going to keep doing this over and over again until we run out of numbers to work with, right? So 3 times negative 3 is going to give us negative 9. And then we go ahead and add those 2 results here, right? So we have a positive 7 plus negative 9 that's going to give us a negative 2. And then one last time we repeat that process, right? So we are going to go ahead and multiply that 3 times the negative 2. So we're going to multiply that, and then the result we're going to go ahead and put right there in our last line. So that is going to give us negative 6, all right? And then, of course, we add, and then we, of course, run out of columns there. So we get as our final number here, we get negative 6 plus negative 6, or in other words, negative 12, okay? And so equally as important as being able to understand how synthetic division works as far as the algorithm is concerned, we also need to understand how to interpret our answer here, right? So the way that we do that is in this way, right? The last number that you get in your synthetic division is always going to be the remainder that you get after doing the division. So here that's going to be a negative 12. The other numbers here, these are the coefficients and constant of your quotient, okay? And the way that I like to go ahead and write that out is starting at this last number here. So that's negative 2. This is written in standard form, and so we would go ahead and interpret that negative 2 as our constant minus 2. And then the next number after that, negative 3, that is going to be the coefficient on our x term. So I'm going to go ahead and kind of write backwards here to get the rest of the quotient here, right? So the first number there in that list is going to be a positive 5. That must be the coefficient on our x squared term. So I'm going to go ahead and say 5x squared, and that represents our coefficient. Remember how we write our final answer. We write it as quotient plus remainder over divisor. So we're going to go ahead and say plus here, our remainder, which is negative 12, over our divisor, which remember from before looked like x minus 3. Okay. So that is one version of our final answer, but one quick thing that we can do to clean this up a little bit is since we are adding on a negative, we can go ahead and change that operation to minus here. So a final result here, just simplifying that as much as possible, would be 5x squared minus 3x minus 2 minus the rational expression 12 over x minus 3. Okay, and that represents our final result right there. All right, so synthetic division, that one took a little bit of a time to explain just because that was our first one in the video, but synthetic division is meant to be a process it's supposed to go very, very, very quickly, okay? And so I'd like to go ahead and demonstrate that right now. So very, very important that we always remember that when we are doing synthetic division, we first have to check to make sure that we have the green light, and we do here because the leading coefficient of our divisor is a 1, the degree is also 1, so we have the green light to do it. But the other thing that we also very much need to make sure that we do is put placeholders in place of the terms that are missing. We said that same thing for long division. We're definitely going to have to make sure that we do that for synthetic division here as well. Okay, and so just kind of going through that process here, if you need to go back and rewatch the last example to remember how the numbers map around, then I would recommend that you do that. I'm just going to go ahead and blaze through this. So drop the 3, and then multiply, and then add, and then multiply, and then add, and then multiply, and then add. Okay, so that process is meant to go very, very, very quickly since you're just adding and multiplying a bunch of numbers here. Now remember that last number is, of course, the remainder, and then the numbers that we got here as the result, these are going to be the coefficients and constant of my quotient here. So I like to kind of work backwards. We have our constant, and then we have our x term coming before that, and then we have our x squared term coming before that. So there's our quotient, and because our remainder is just equal to 0, we're not going to go ahead and write 0 over our divisor. We're just going to go ahead and write this as the final result there for the problem. In the next example 6, we are going to go ahead and divide synthetically here, but we do need to make sure that we have everything written in standard form before we begin. The order of standard form, and also including those placeholders if we need them, that's going to ensure that we don't make any errors when it comes to the synthetic division here. And so, again, just kind of doing this really quickly, we drop, and then we multiply, and then we add, and then we multiply, and then we add, and then we multiply, and then we add. Okay, so remember that last number, of course, is the remainder, and then we get a final result here of negative 16 plus 0x, and then plus your 9x squared here. Now, that 0x, of course, is not going to be something that we're going to leave in our final answer. We're going to simplify this as much as possible, and so we end up with a final quotient of 9x squared minus 16. And, of course, the remainder is 0 there. Okay, so you can see that that is meant to be a very, very fast process. Again, making sure that you have placeholders in place of missing terms and making sure that you write your polynomials in standard form is very important before you continue to do synthetic division. And, again, the whole point of us talking about polynomial division is that it can make it easier for us to do problems like we saw in the last video where we were trying to find zeros and graph polynomials and that kind of thing. But it's an unfortunate case that sometimes we are faced with a polynomial that does not factor, at least it doesn't factor in the way that we talked about with our previous factoring methods. So what we're going to need to do is use polynomial division, and in conjunction with a couple of these theorems that we're going to see here in this next slide, to make some sense out of how we can factor polynomials that don't seem like they can factor for us. So we have two theorems here. One is called the remainder theorem. The other is called the factor theorem. And so, of course, a couple things to point out here. It says the remainder r after using synthetic division on f of x by the factor x minus k tells us a lot of things, right? So first of all, if you do synthetic division, then whatever the remainder is, that is going to be the function evaluated at that number that you used with synthetic division, right? So we'll see a more concrete example of what we're talking about here in a moment. And then the second thing, that's called the factor theorem. So it says if your remainder is equal to 0, then that means that your polynomial is divided evenly, and that is going to mean that the factor x minus k is just that. It's going to be a factor of f of x. Without a remainder there. So I'd like to go ahead and demonstrate how that process works here by taking a look at a couple of examples here. So example 7, it says use synthetic division to evaluate the function f of x at x is equal to negative 2. Okay, so in other words, you're basically being asked to find f of negative 2. Before, we would just simply plug in negative 2 here, but the remainder theorem says that if we do synthetic division, then this is going to give us a way to figure out what this function is going to be without having to reach for a calculator and meticulously plug in negative 2 everywhere we see an x. Okay, that might be a little bit of a pain to have to do as a calculation. Okay, so synthetic division offers us a really easy way to figure out what this function would be. So let's figure out what that is, right? So iterative process here, I'm going to drop the 3 and multiply, and then add, and then multiply, and then add, and then multiply, and then we, of course, add here, and we end up with a result of negative 9, okay? And so, again, by the remainder theorem, what this is going to be, the remainder here, of course, was negative 9, so what we're going to say here is that f of negative 2 is simply just going to be negative 9, okay? And that's pretty handy, right? So that kind of is going to prevent us from having to reach for a calculator every single time we want to evaluate a polynomial function at a specific value. We're just going to go ahead and perform the synthetic division, and then whatever the remainder is, that is going to be the output of this machine when we input that number -2. In example 8 here, a similar problem. It says use synthetic division to show that x equals -3 is a 0 of the polynomial, and then use this result to factor the polynomial completely and then list all the zeros. Okay, so you can see here that I've already got our synthetic division set up for ourselves, so I'm just going to go ahead and execute that. So going through the algorithm here, you drop the 2 and then multiply, and then you add, and then multiply, and then add, and then multiply, and then take a look there, right? We ended up with a remainder of 0, so that's pretty nice. And so because the remainder is equal to 0, the factor theorem is going to say that the factor that this 0 came from, which that factor, of course, would look like x plus 3, we know that that is going to be an algebraic factor of the polynomial that we started with, right? And so what we do here is we go ahead and say that f of x, or a polynomial, can be written as the factor x plus 3 times, and then we have our quotient here, right? So we have 2, 5, and 3. That is going to be 2x squared plus 5x plus 3. And so that is going to be a factorization of our polynomial. And so what we now need to do is just go ahead and take a look at the quotient here and then ask ourselves if that is something that can continue to be factored. If it can be factored, then we're just going to factor it in the usual way. If it cannot be factored, then we're going to have to do synthetic division again to factor it, just like we did for this last iteration of the process here, right? So I'm going to go ahead and write the x plus 3 out front, and then I'm going to factor this trinomial 2x squared plus 5x plus 3. I'm not going to dive deep into why this is the factorization. Again, I've made a couple of different videos that discuss how we can factor polynomials, so we'll go ahead and just leave it there. So the complete factorization that we end up with here is going to be this factorization right here, in which case, remember that these have zeros associated with them. So if we were to set each one of these equal to 0 and solve, in this first case, we would get x is equal to -3. That's something that we started with in the problem, so that's pretty good. But we also get zeros of -3 over 2, and then also x is equal to -1 here. So these are the 3 zeros that we should be ending up with here in this process. And that makes sense because the degree of our polynomial originally was a 3, so it makes sense that we end up with 3 different zeros. And then as far as the last example in this set of notes is concerned, we're going to go ahead and show that the algebraic factors x plus 2 and x minus 3 are indeed factors of this polynomial f of x that they gave us, okay? And so, of course, the way we do that is we use the remainder theorem, okay, which says, of course, that if we do the synthetic division and the remainder is 0, then that means that these polynomials divided evenly, and then factor theorem will say that these are going to be factors of our process, or of our polynomial, right? So I'm going to go ahead and repeat that process here. So drop the 1, and then we're going to continue with that iterative process here. So -2 times 1 is -2, and then we add, and then we multiply, and then we add, and then we multiply, and then we add, and then we multiply, okay? And just to make sure that I am doing this correctly here, I might have made a sign error somewhere. So actually, I did make a sign error. So let me do a back step here, right? So that was not supposed to be -5. That was supposed to be +5. And then that's going to be -10, and then it's going to give us 12, and there we go. Okay. The reason that I knew I made a mistake is because where I was headed was a remainder that would have not been equal to 0. That would have meant that x plus 2 would not have been a factor of our polynomial, and then we wouldn't have been able to continue, right? So just a little bit of a red flag there in that problem. We do see a remainder of 0 there. Now, I've gone ahead and written the next synthetic division there because, again, we just showed that x plus 2 is a factor of f of x. So x plus 2 is a factor of f of x, okay? But if x minus 3 is also a factor, then that should be a factor of what we had remaining here after doing synthetic division the first time. So that's why I've gone ahead and just immediately set this up, and we're just going to go ahead and repeat that iterative process, but with this, this remainder that we got, right? So we'll drop the 1, and then multiply, and then add, and then multiply, and then add, and then multiply, and then we do definitely see that we get a remainder there of 0 as well. Okay, so that is enough to show that x minus 3 is a factor, and again, that's by the factor theorem. If the remainder is 0 after synthetic division, then what we have here is an algebraic factor. Okay, and then what we are left over with here is a 1, a -3, and a -4, and so we're going to interpret that as the rest of our factorization. Okay, and so we're going to go ahead and write our polynomial f of x in terms of the two factors that we just proved that we have, right? So x plus 2 times x minus 3, and then times something. What is that something? Well, that's what we're using our numbers here as our result from. So that's x squared minus 3x minus 4. And then let's see if that can continue to factor. I believe it can. We could factor that into the product of two binomials, and I think some combination of 1 and 4 might work. How about a negative 4 and a positive 1? Okay, and so the complete factorization of f of x is x plus 2 times x minus 3 times x plus 1 times x minus 4. Okay, so those are all the remaining factors there, and then each one of these factors corresponds to a 0, and so we'll go ahead and make a complete list of zeros. Again, just by setting each one of these factors equal to 0 and solving, we would end up with the following solution set. We would have x is equal to negative 2 and positive 3. Again, those are ones that they basically gave us at the beginning of the problem, but we're now seeing here that we also have zeros of negative 1 and positive 4, and those would account for all the zeros that we have here in this problem. So we can get a complete factorization by using the synthetic division and the remainder and factor theorems, and we can also go through and find our zeros. And again, we're going to stick with this process for any polynomials that we're given that we don't quite know how to factor from the get-go. Okay, so we are just adding tools in our toolbox for being able to make some sense out of polynomials that we need to find the zeros for, to graph. Again, synthetic and long division, these are very, very powerful tools for being able to do just that. So that's all I have for this video. Thank you very, very much for your attention. As always, if you guys have any questions whatsoever, please feel free to let me know. But I will speak to you guys in the next one.